This lesson is about learning about the concept of Markov chains. Now, Markov was a Russian mathematician, and he looked at the probability associated with a system as it made various transitions. Now, that sounds a little bit complicated, but let's look at a specific example. The example I'd like to look at is in your textbook, and I'll put that under the camera now. And it's the example here on page 57. On page 57 of your textbook, it says, in Palmdale only 2 brands of soft drink are sold, blue or red. I'll let you keep reading that. You can pause the video if you want to, but have a read of that example. I'm going to write some of the details on the paper. So initially, we've got blue and we've got red soft drink. And these two companies are competing. And at the moment, 50% of people like blue and 50% people like red. But as the months go on, as time goes on, some people decide to change which brand of soft drink they like. And as you can read in the example, at the end of each month, 40% of people who drink blue change to red. So 40% change to red. That means 60% stay with blue. Okay, they're happy customers. On the other side, 70% of red drinkers change to blue. You can read this in the example, meaning that 30% stay with red. Okay, so let's set up a bit of a pattern here to see what happens as the months go by. Well, we'll make a table here. At the start, we've got blue and we've got red. 50% and 50%. 50% like blue, 50% like red. We could call that, and you'll see why I'm calling this name later, let's call that S0. S stands for the state of the system. So S0 is the initial state. Now let's have a look at after 1 month. We're going to call that S1. Now, to work out what happens after 1 month, we need to consider these changes that we looked at. For blue drinkers, 60% of them stayed with blue. So that would be 0.6 lots of 0.5. This is the 60% of these guys. So 60% of, multiply, of these guys stayed with blue. But also some others came to blue. The others that came to blue were the 70% of these guys that changed over. So we could have 0.7 lots of these guys that actually now drink blue drink. The red, well, some of the red stayed with red. 30% stayed with red. So 30% of the current percentage, which was a half or 0.5, they drink red, but also some of the blue drinkers changed over to drink red. So the total number of people or proportion of people drinking red will be those that were drinking red and stayed with red, plus those that moved over. Now those that moved over were 40% of these guys. 40% changed to red. So 0.4 lots of the current percentage of those drinking blue that changed to red. Now if we work out these numbers, if you type these into your calculator, you'll find that this is equal to 0.65 or 65%, and this one is equal to 0.35 or 35%. Okay, so now our percentages are blue has now changed from 50%, now blue has 65%. Red no longer has 50%, they're down to 35% of the market share. So let's have a look at what happens after 2 months. After 2 months, let's go through the same process. The blue drinkers, 60% stay with blue. So 60% of the current blue drinking population, which is 0.65, okay, this number here, plus the proportion of red drinkers that change to blue. So 70% of these guys change. So plus 0.7 lots of 0.35 actually change to drinking blue. You can see that these guys are going to start dwindling down. Now let's look at the red drinkers. The red drinkers, 30% stay with red. So that is 30% of the current red drinkers, 0.35. But some of the blue drinkers change over to red. 40% of these guys change over to red. So we'll have 0.4 lots of, our current percentage is 0.65, will change over. Now if you work out these percentages, type these into your calculator, and you'll get 63.5 or 0.635 and 36.5%. So here we see a pattern, and this is actually what's called a Markov chain. We've got a chain of values. They started with 50%. They went up to 65%. Now they're at 63.5%. The red drinkers went 50, 35, 36.5. And we could go on and on after 3 months, 4 months, 5 months. Now, before we go too much further, this is obviously going to get very complicated. So one of the ways we can simplify this is to use matrices. Now remember, matrices are just a structured way of containing information. And so what we're going to do is we're going to set up our initial state of the system matrix, and we're going to call it S0. S0 is the initial state, which will be the 50% and the 50%. This is 50% blue, 50% red. We also set up now what we call our transition matrix. Our transition matrix is the tricky one to set up. And because we've got some changes here to represent. We're going from and we're going to. And here's our matrix. We're going from blue, or we're going from red. and we're going to, and I'll just give myself a bit more space here, we're going to blue or to red. So we're going from blue to blue, or we're going from blue to red. So when we look at our initial percentages here, what proportion of people, when they transition, this is a transition matrix, what proportion of people transition from blue to blue? In other words, stay with blue. So that is 60%. So that means how many would go from blue to red? Well, it'd have to be the remaining amount. So if 60% do that, then 40% will be here. What proportion of people go from red to blue? Well, in the question we read that 70% of red drinkers change to blue. So that would be 70% there and 30% here. So this is now what we call our transition matrix. Now, this is our initial state. If we want to work out the state of our system after one transition, if we multiply our transition matrix T multiplied by S0, that is going to be 0.6, 0.7, 0.4, 0.3 multiplied by S0, 0.5, 0.5. Now a little bit of revision here, remembering your matrix multiplication. In order to multiply these matrices, we multiply the top row elements by this column elements. Then we multiply the bottom row by the column. So if we look at these numbers, watch carefully. 0.6 multiplied by 0.5, look closely up here. 0.6 multiplied by 0.5 plus, according to matrix multiplication, 0.7 multiplied by 0.5. Compare that with up here what we did. 0.6 times 0.5 is what we had here. 0.7 plus 0.7 times 0.5 is exactly what we had here. So this, when I multiply that row by that column, I get 0.65. When I multiply the bottom row by that column, I get 0.4 times 0.5, there it is, plus 0.3 times 0.5, there it is. So I multiply this row by this column, which is the same as what we did up here, and we get 0.35. Now you can grab your calculator. You can also do that in your calculator. Go to your menu, go to matrices, and I suggest you put in matrix A as a 2 by 2 matrix, and here we go, we'll put it in 0.6, 0.7, 0.4, 0.3, and we'll put in our matrix B. I'm going to put my matrix B as my initial state, so that's a 2 by 1 matrix, and its initial state is 0.6 and it's 0.5 and 0.5. Better change that one. Okay, now we go back out to our run mode, and we're going to go matrix we're going to go matrix A multiplied by matrix B. And you will see that you will get the 0.65 and 0.35 as your state. Okay, now if you go ahead, you can try the after 2 months. If we wanted to work out after 2 months, I'll do it over this side. If we want to work out the state after 2 months, so we'll call that S2. S2 will be the transition matrix multiplied by the state after 1 month. Okay, so the transition matrix is taking S1, it's transitioning S1 to becoming S2. So that would be 0.6, 0.7, 0.4, 0.3 multiplied by the state in the last system, which was 0.65 and 0.35. Okay, so this is the transition matrix multiplied by our previous state, which was S1. Multiply these, you'll notice 0.6 times 0.65, that's what we had up here, plus 0.7 times 0.35. So this matrix multiplication is exactly the same as what we did logically here. The bottom row, 0.4 multiplied by 0.65 plus 0.3 multiplied by 0.35 gives us 0.635 and 0.365. And so that is the state after 2 transitions. That's the state after 2 transitions. Notice something here important in the transition matrix. What do the columns add up to? The columns add up to 1. Okay, because these are percentages or probabilities, then and because these cater for every possibility, so it's either red or blue, there's no alternative, then the probabilities or the proportions of each of them must add up to 1. So the next video we'll look at what actually happens in the long run. What happens in the long run after lots and lots of transitions? And we obviously need a shortcut way of doing this, because we certainly don't want to be doing long calculations like this all the time. So stay tuned.